So here's a constant acceleration. I'm just going to go. Boop. I cheated. Right, you can quickly write down those equations if you want to, right? So we're going to do the first 3 seconds. So I'm just trying to keep it as clean as possible here. So it's labeled. We're going to do the first 3 seconds. Okay? And we're going to do that. Okay, so that's going to tell us what our velocity is. I need to know what my velocity is after the first 3 seconds, and then I need that velocity then to figure out what the position is after the first 3 seconds. Okay, so at this point right here, let me get the notes out. I'm going to plug in the values that we know. Okay. So in this equation right here, first 3 seconds, right? I know all these variables, right? I know what A naught is. It's 100 G's. G's is gravity, right? Right? And so then we're going to see, what are we doing this in? We're doing this in metric units because we're talking about kilometers here, right? So we'll do this in metric. So that's going to be 9.81. So it's 100 G's. So that's going to be 100 times 9.81. That's what A naught is. Okay. T, we don't know. That's going to be 3 seconds, but right now we're just going to put it as T. T naught is 0, right? Because it's starting out from rest, right? And that's our initial time is 0. That's 100 G's, right? And so the velocity at T equals 3 seconds. You would just plug in a 3 for that T right there. That would give us 29.43 meters per second. Okay, so I just plugged in what the A naught was, and then I just plugged values into this. Right, T naught 0. Oh, V naught 0 as well. I guess I'm going to cross them out over here. This starting out without any velocity, so that V naught goes to 0. So I just plug in 100 G's basically times T, which makes sense. You take acceleration, multiply by time, and it'll tell you what your velocity is, right? So 29.43 meters per second. Then we come down to position right here. Let's plug in all our knowns here. That's going to be 100 times 9.81 times T times T squared, right? T naught 0 over 2 plus V naught is 0. Right, so this V naught right here is 0, so I'm not going to even write that down, right? And S naught 0. And so this guy, you just put this in your calculator. Boop, beep, boop. S at T equals 3 seconds. Tells us that our position after 3 seconds is 4,000. Ooh, is that a 4 or 9? I can't read my own writing. 4414. You literally just carry that out. You put a 3 right here in that T, and you get that. So that's the distance it's gone after the first 3 seconds. So in this is its velocity after 3 seconds, and that is its position after 3 seconds. Those become the initial ones in the next equation, which we'll jump to next. So that's just the first 3 seconds. So let's switch over to the decel. Deceleration. Hopefully I spelled that correct. All right, let me jump over to that. This also is going to be constant acceleration. I'm going to copy those guys again. You heard me talk about calculators, right, for like college, not a huge deal. The other thing that's really awesome are tablets. Right? I know you're all poor, and you can't really get tablets, but I was poor once too. If the university, well, yeah, I'm still poor a little bit, right? That's okay though, because we're in college. Who cares if we're poor, right? I'm serious, because you usually have this better lifestyle, right? But tablets are awesome, right? So if you have one or have an opportunity to get one, it's great for taking notes. You put all your notes in one place. You can put your books on there. You can do everything. They're freaking amazing. They make homework assignments super clean to make and grade and stuff. They're awesome. Okay, so the deceleration, this is -4 Gs. Right, this is all review for you. Right, and again, it's constant. Right, so in this case, we do the same thing where we have to go, we're going to go from acceleration, which is -4 Gs, to velocity to then position, right? So we're gonna use that same method here. But now it's a little bit different, right? A naught is gonna be different. It's gonna be -4 Gs. Now there is a T naught, right? What's our T naught gonna be? 3 seconds, right? Because this one's kicking in after 3 seconds, right? And then what about V naught? V naught's gonna be the V that we got before, right? So at the start of this stage, our V naught is gonna be 2943 meters per second, right? So now we actually do have a V naught. Same thing down here in this S. My A naught is gonna be -4 Gs. My T naught's gonna be 3. My V naught's gonna be this V naught that we got up here, T naught. And then S naught in this case is just gonna be that 4414.5, right? Because at the beginning of this stage is the end of the last stage, right? And go from there. All right, so let's do that. A naught, again, it's gonna be -4 times 9.81. That's A naught, that's -4 Gs, times T minus 3 seconds, plus V naught, which we just had, 2943. Right? That is my V equation. Right? We'll come back to that later. Actually, technically we don't even need that. So, because that would tell us what the velocity was at a certain time, but we don't actually. After that, we're after a certain distance. We're after 15 kilometers. So let's plug in the values to this one. A naught is -4 times 9.81. That's A naught times T minus 3 seconds squared. All of that over 2. Plus V naught again is 2943. 2943 times T minus 3 seconds plus S naught, which is 4414.5. 4414.5. Okay, and that's what S of T is. Okay. The problem statement says, we haven't really gotten to that yet, but what the problem statement says is how long does it take to get to 15 kilometers? So what do you think once we get to this point right here, what do we do? Is that equal to 15? 15,000. Put it in 15,000, right? Because you got to be careful of the units. I also should point out, I am very loose with the units, okay? If you can see, I haven't written down a single unit yet, right? Don't do me. Don't do what I do, right? Do what I say, not what I do. I'm a doctor of this material, right? So I am very, I think Kirsten's the opposite. Dr. Madison's the opposite. I think she's very like, you gotta write down your units. I was like, I'm a college kid. I do what I want, right? Like I do what I want. I use units when I want to use units. But what I'm very religious about is just keeping everything in the right units, right? Everything's in meters, everything's in seconds, everything's in newtons, everything, right? I always just do it that way. And you just gotta be careful about it. If you have problems with it, if you're going, oh my God, I keep getting wrong answers because of the units, start putting units on everything, right? And that's nothing wrong with that. Absolutely do it. It just means you're weak. Okay, but do it, right? I mean, everybody's got their own thing, right? You find what works for you and you do what works for you, right? I get bored. I get bored writing units all the time, so I just say, okay, well, I'm just gonna leave them out. So, okay. You're not weak. It is literally it's you do what works for you. You find what works for you and you do what works for you, right? And that's That's great. Go for that. So then in this case, right, if you set it equal to 15, you'd get the wrong answer. You have to set it equal to 15,000 because it's 15 kilometers, right? And you get to this point right here. It's like, oh my God, look at this. Oh, it's a quadratic. Oh my God, oh man, what do I do, right? Many of you will simplify this thing, you know, down all the way down until you see like the form of the equation that you need to use the quadratic formula, and then you use the quadratic formula to solve it. Shame on you. Don't do that. Don't do that. Right here, in this exact form, whip out that calculator in the solver and go boop, 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 and then hit the thing and then go calculating, and then boom, it'll tell you what t is instantly. Right? And then you can look at your calculator, it's like, okay, did I enter that correctly? And you're just looking, yep, I entered that correctly, and oh, there's the answer right there. Even a TI-84 will do that. That's my take on it. Is like, don't waste your brain power, right? What limited brain power you have, don't waste it on trying to solve, like doing the quadratic formula on this thing. Just, you have a tool, you're allowed to use it. I want you to use it. Plug it right into the calculator. You can put it into that exact same form, just like that, right? And then even the divided by 2, right? Like that's the easy one. That's -2. I could simplify that down to -2 times that, but don't even do that. Who cares? Like I just had to waste brain power to think about that. Just plug that sucker into your calculator, and then out will pop 2 answers for t, right? And the one you're gonna add, then you gotta use a little bit of reason for what the t is you want. You'll get t is equal to 6.68 seconds is what you get for the answer there, right? And that, in my mind, on your homework, on an exam, if you get to that stage right there and you just jump down there and gave me t, perfect, correct, applause to you, right? You do have to write out the equation in its, like, I would recommend that, is writing out the equation in its final form that you're going to solve. Absolutely do that, because if you write down the t equals 6.68 seconds and that's wrong, then I can't give you any like extra credit. Like I can't be or partial credit. I can't go, oh look, it must have entered something in the calculator wrong or something like that. I can't do it. If you just give the answer, I'm like, I don't know what you did, right? I have no idea. But if you write down your equation, I can usually find what it is that went wrong. Okay. Cool beans? All right. Any questions about that? I mean, and also I want to point out too, right? Like, as you've seen, right? I don't have the cleanest handwriting. I don't have the cleanest handwriting, but my solution is pretty structured, right? It's easy to follow, right? And that's what I want you to strive for, is just to really just lay it out, just like, oh, you know, let me just make this as clean as possible. As engineers now, that's part of our job, is to make things, you're gonna have all these complex thoughts, and we have to take it and put it down so that somebody can follow the work and solve the problem. Yes, sir? Yeah, absolutely. That's a great question, right? I did this. We didn't use it, right? We didn't use that equation, you know, and we didn't need it. And so you absolutely, if you see it before and want to go right to here, yeah, we didn't need that velocity, then go right to there. We needed the velocity equation in the first part of the problem because I needed to know what V naught was coming into this one. But this second one, I don't need it, right? If there was a follow-on problem saying, well, what was the velocity at the point, you know, that it hits 15 kilometers, then you would need it. Then I'd take that 6.68 seconds, plug into that equation, it would tell me my velocity is. That's a great question. Yeah. Yep. Okay. The question about one? Next one. Okay. All right. Mass release from rest. Spring is unstretched. There are my equations, and let me. Okay, so this one's, oh, you son of a bitch. Oh, okay. So this is a problem where they give us the acceleration of function of position. A is a function of s, right? What does that mean? It just means in my equation on the right-hand side, 32.2 minus 50s. So s is a variable that can be substituted in there. Later on, so this is one of those things, we're just doing kinematics. We're not looking at how forces result in motion yet. So we're looking at we're given this equation. We're just doing integrals and stuff to solve these things. Later on, what we're going to strive for is we're going to derive this equation, right? And you should recognize some components in there. What we're going to do, the next part where we do kinetics, like in a couple weeks, what you would do is you'd say, oh, here's this thing. Let's look at the forces acting on it. Well, I've got, mass times gravity going down, and I've got, K times S going up, and the sum of those is equal to mass times acceleration, right? That's what this is, right? You should see that's G, 32.2 coming down, right? And then 50 times S is the spring constant. So don't worry about that right now. This is a little foreshadowing. It's like we're going to start out with problems where we go, all right, this isn't given to us. There's a mass release from rest. How far does it go? And so what you would do is you go, oh, I'm going to sum the forces over here. I'm going to set forces equal, sum of the forces equal mass times acceleration. I'm going to come up with my acceleration equation by dividing by mass. And then what you would end up with is an equation like this. And then after that point, you do kinematics to get the problem, to solve the problem, right? The other thing that you'll see too is even that problem, many of you, how would many of you solve that problem right now? A spring, it's being dropped, it's asking about different velocities. Work energy, right? This one screams work energy, but we'll talk about solving those later. Right now, we don't know about those. This is future stuff. So right now, they just give us this equation, we have to solve it. Okay, so this is acceleration, a function of position, right? In our cookbook up above, we have a method for solving accelerations as a function of position, and so you can look up at what we did. Acceleration, a function of position, right? And we just did this. We said what did I do here? What did I do? Oh, I went back too far. It's velocity. Yep, so we, you could look up in your previous notes. I'm going to rewrite like kind of what we derived. Acceleration of function position is equal to dv dt. We couldn't really do that one right because you got a v, a t, and an s. So that's where that chain rule comes in. This is what we laid out in the solution procedure. This is going to be, you basically multiply by ds over ds. So it'd be dv ds, ds dt. ds dt is the velocity. And so then we have a of s is equal to dv ds times v. Put the ds's together. A of s ds is equal to v dv. You could jump right to that too if you wanted to. I just wanted to kind of rederive where that came from. Careful of these, don't just integrate with respect to time, doesn't work, right? Oh, so by the way, I may have left that out. What we're after, and this is clear, like I've written them in the form right here. In your homework, I want you to do this where you say, all right, you're gonna read the problem statement, and you say, what was I given and what was I finding, right? Just to make it really clear what you're after. In this case, we were given the acceleration equation, the function position, and we're asked how far does the mass fall and what is the max velocity. We're asked after both of those things, okay? And so first of all, I need to go acceleration to velocity and the velocity to position, right? So A of s ds is v dv. I know what this acceleration equation is. This A of s, it was given to me up above. All right, A of s, this is going to be 32.2 minus 50s ds. I'm going to integrate that sucker, and that's equal to v dv. And I'm going to integrate that sucker. Okay. When you have those ds's floating around, you got to do some integration. Okay. This is going to go from 0 to s. Right, I'm after that s right there. So right now we don't know that we don't know that part of the definite integral. We're just going to leave it as a variable that, and this is going to go from 0 to v. Okay, even at this point right here, right, those are easy integrals to do. Right, they're not bad. Right, but what would I really do? I'd put that sucker in my calculator. Okay? I would get to that point and I would say, oh man, I don't want to make any mistakes. I don't even want to think about doing an integral. Let me just do the integral on the left-hand side, do the integral on the right-hand side. TI-89 will kick it out to you in a beautiful fashion. Right? It's not hard, right? So So then you carry out those integrals. 32.2 s minus 50 s squared over 2, right? You can do that one in your head if you like to do that sort of thing, right? And the right-hand side is going to be v squared over 2, just an integral of v to v. Right, great. So that's where we're at right now. Right, this is what we talked about. I mentioned this in our solution procedure. When you carry out those integrals, you're going to have some s's floating around and some v's floating around. What I want is the v isolated, because what that'll give me, that v isolated will be a velocity as a function of position. It'll tell me what the velocity is, which is v, given an s. So at this point, I solve for v, right? And again, you can put the sucker in your calculator, or you could just, it's easy, multiply by 2 and take the square root. But so v of s ends up being equal to the square root of 2 times 32.2 times s minus 50 s squared over 2. And that 2 is multiplied by the whole thing. I'll keep my guy going on that. Okay, so that's my velocity function position. So let's take a step back here and just think about what this thing is going to do, right? So this is a mass on a spring. I got a hold of that sucker, and we've raised it a little bit, if you will, and I'm going to let go of it. Actually, in this case, it's even in neutral position. And I let go of it. What's it going to do? It's going to go down. Then what's it going to do? It's going to go up. It's going to go down. It's going to go up. It's going to go down. Right. So this is an oscillation. It's going to oscillate. It's going to vibrate. Right. And that's kind of like the fundamentals of vibrations when you get into it. But the solution is going to be right. The solution is going to look like this. Okay. And in fact, that's going to be a sine wave or a cosine wave. It's probably going to be cosine is what it's going to be. It's going to have initial position, but that's right. But it's going to look like that. So if I'm after, the question says, how far will the mass fall, right? When am I going to find when the maximum distance that this thing's fallen? What's the velocity going to be? 0, right? It's going to be right down at the end, right? Say it's down is that way. So it would go like this, start right here, and then it would go boop, right there, and then be on the cusp, right? It would go down, it would be 0 velocity, and then it's going to come back up the other direction. So at this point, if I want that max position, what I do is I set this equal to 0, right? That's when that's going to happen, is when that velocity is going to be equal to 0. Okay, so we'll make a little note down here. Okay. Max velocity would be equal 0. What do? Put it in the calculator, set it equal to 0, solve for s, right? And then out it pops the answer. S ends up being equal to 1.288 feet. Again, this is me being loose with units here. Right, that 32.2. Yeah, actually it says feet per second squared, right? Feet per second squared, it was given to us up there. So you put everything in terms of feet per second squared, and you get that position. It's 1.288. Okay. All right. When we get the max velocity, the second part of the problem, that's the first part of the problem, says what's the max position, right? The second part of the problem says what is the max velocity? When are you going to get the max velocity? What's that?
Should it say max distance from the stretch spring?
Yeah, that's. Let me finish. I wasn't done yet. I'm just joking, dude. It was absolutely an accident. That's my favorite joke. That's another favorite joke that I will always use, whether or not it's funny, is that if I make a mistake, I'll just say, I wasn't done yet. Yeah, max S. There we go. There we go. Yeah, now I'm done. I just want to say, what's wrong with what I wrote is what I was just going to get to, man. Yeah, that's right. Thank you for pointing that out. Yes, sir.
Would the max velocity be like when S
Close, other way. Yes. Yep, when the acceleration is equal to 0, right? Right? When it's right on the cusp of accelerating one way versus the other way, your velocity is going to be maximum, right? So you do the same thing, which we're going to set acceleration equal to 0, and that will tell us, well, we could do that right now, right? We have acceleration as a function of s, right? So we could say, oh, let me just add that, max, oh my God. Max velocity when a equals 0. Okay. And so we have the acceleration equation already. It was given to us. Acceleration a function of position. We're going to set that equal to 0. And that's 32.2 minus 50s. It's all for s here. S ends up being equal to 0.644 feet. Right? That's not the answer. That's the position when the acceleration is going to be equal to 0. I then take that and put it into my velocity equation up above. So I take that and put it in there, right? So my v of s equal to 0.644 ends up being equal to 4.55 feet per second. I'm going to box that with this. Cool. And so I was saying, in this kind of a good example of this is, there's a lot of like feeling around. You're like, okay, well, I know that the velocity is going to be, that my max velocity is going to be acceleration equals 0. My s is going to be max for this thing's happening. I'm going to use this integral. I'm going to use this integral. And then there's different ways to do it. So sometimes you can do the same problem 2 different ways, right? And it's all great. There's not a wrong way to do it. If you can do it both ways. So I really think the first part of this class, the first portion up to the first 2 exams is the hardest. And then after that, it's just so structured. You don't have to really even think. You're just like, all right, this is what I'm going to do. I'm going to apply this. I'm going to use this method. I'm going to step through it, and it's a little bit cleaner. So if you're feeling a little like, oh my God, you're not alone. I do it too. I'm teaching the class. I feel the same thing. I feel the same way. Uh-oh. Okay. Let's go down to the next one. How much time we got? Oh, you got 14 minutes. We got it. Okay. Rocket car. Lots of rockets involved. Trying to appeal to you guys. They're cool. Rockets are cool, right? Rocket car accelerates as a function of time till it reaches 400 meters per second. So it's going to be acceleration of function of time. Haven't seen one of those yet, so it's our first one of those. Until it reaches 400 meters per second. Then water brakes are applied, and it decelerates as a function of velocity until it reaches 100 meters per second. It's actually pretty cool. Well, maybe on Friday we'll watch some videos of this. They did some tests back in the day to see the maximum acceleration that the human body can take without dying. And there was a guy that they strapped to a rocket car with water brakes, and then they get him going really fast. And actually where he's hitting the max accelerations are when he's decelerating, when he hits that water, and it's like, when his eyes pop out of his head and stuff. They don't really come out, but they get close, I think. But we'll look at it. And he did it over and over and over and over. This guy. This is the whole thing. He was a crash test dummy. That's what we used to do. As long as you volunteer, we're doing it. We'll look at that later. So that's what's happening. So this is, so the second part of the problem, the water brakes. The whole point of the water brakes, in his case, what they were doing is they're hitting a puddle of water, like a pool of water, to slow him down, which we would do the similar deal. Okay. In that case, it's going to be acceleration of function of velocity. We're going to do acceleration of function of time for the first part, and the acceleration of function of velocity afterwards. And we're supposed to find the total distance that gets traveled during that time. Okay. So let's do the first part. Let's do the acceleration. I will point out that in the past I've had a TA grade, and the TA grader was going around and docking people for not showing all of their math, and then nobody let me, and even though I was on the other hand going, don't show your math, just use your calculator, and people were getting docked. So if this starts happening, let me know. We'll go after it. We'll storm into Axel's office together. Like, what are you doing? I told him to do this. Right? So this is going to be a function of time. Right? So a of t is going to be equal to, they tell us this, 30 plus 2t. Right? That's equal to dv dt. Right? And I take that dt on one side, move the dt to the other side. 30 plus 2t dt is equal to dv. I integrate. Right? This thing is going to go from 0 to t, and this is going to go 0 to v. Carry out this integral. Pretty easy one again. This is going to be 30t plus 2t squared over 2. And the 0 goes away. This is equal to, if you carry out v dv, that just gives us v. There's our velocity as a function of time right there. Okay. So at this point right here, so the problem statement, I was just looking up at the problem statement. The problem statement says, all right, we're going to go in this stage, this acceleration stage, until we hit 400 meters per second, okay? And then the water brakes are applied. So at this point right here, I can figure out how much time it takes to get to 400 meters per second. Then velocity is a function of time. So I set that equal to 400, and it'll tell me the time it took to get there. All right, we're going to need that later. 30t plus 2t squared over 2 is equal to 400. Right? Plug that sucker in your calculator, and it will tell you that this is t equals 10 seconds. Okay? So that gave us velocity, right? But we still got to keep going. We need to see how far it traveled in that same period of time, right? I still need to do that. So then now at this point, I go down and we got acceleration to velocity. Now let's go velocity to position. Let me come over here, say v of t. Let's see here. All right. V is equal to ds dt. All right, oh, and then we put that dt on the other side. So v dt is equal to ds. My v I just got that equation, right? And that is this 30t plus t squared. I'm going to go ahead and simplify. I'll stick with it. I'll stick with it. 2t squared over 2, just because who wants to simplify? Not this guy. We're going to keep it as complicated as possible. dt I'm doing that right. Yep. Okay. Yep. Is equal to ds. And that's going to go from, integrate both sides. This guy's going from, we'll get to that in a second. This guy's going from 0 to SF, the final position. That's what we're after, that SF that's floating around up there. Okay, and then what do I put in the bounds of this guy? You could put in 0 to t, and then you'd have s as a function of time right here. Absolutely, you could do that. That's what we did before, like on my upper bound of my integral. Absolutely, you could do that. The other thing is I know how much time this stage is going to take, right? And that's 10 seconds. So I could just slip in. Let's do it this way right now. Let's slip in a 10 right there. Right? That's this guy. You don't have to put that in right now. You could leave that as a t, and then you end up with a function, and then you can plug the t in later. But I just wanted to show it slightly different here. I could put in that 10 seconds there. I know it's going to go from there to there. And so in my calculator, I would put this sucker in just like that. Right? And then it would tell me carry out that definite integral, and it would give me my answer for what this is going to be. And what this gets after the fact, it gets SF is equal to 1833 meters. Okay, so all of that was to get, all of that was just to get what my, how far it travels during the acceleration phase, right? To get us out to this. And that again, that's the most, that's very much review, right? You're just integrating with respect to time on the velocity and the position, right? And it gets us to there. The next stage, though, is now is something new, right? It's the deceleration. Let's jump down to the deceleration. That's the water brakes. Deceleration. Excel a function of velocity. Okay, it's that part of the problem. Okay, so then there's a couple different ways to do this. This is what I was saying before. There's a bunch of different ways to do it. I'm going to do it the shortcut way, and then later I'll show you. This is the long way. Is the non-shortcut way. So there's two different ways to do it. Let's do it the shortcut way because I can and I want to. Okay, and then the long way is on the next page. Did I give you the long way on this next page in your notes? I did. Okay, so you can kind of see the long way. We're gonna do the shortcut way, which is kind of jump into acceleration. Yeah, well, let's do it here. And then whether or not you'd see that there's a shortcut, it's fine. You get to the same answer. Acceleration, a function of velocity, is dv is equal to dv dt. Again, got too many things floating around, so you do the chain rule. dv ds dt. This is just velocity. We've done this a bunch of times now, so this is just going to be dv ds times v, right? And at this point, kind of rearrange everything and get in terms of ds. ds is equal to v over acceleration as a function of velocity, dv. Okay, this is that shortcut. We can skip the velocity and go straight to velocity as a function of position, which is what we're going to do here. And I laid that out in the notes that you have this option of doing this. You can do this little velocity as a function of position thing. So at this point right here, right, I'm going to integrate both sides. So this is going to be integral of ds is equal to integral of v over the acceleration equation. So at this point, that AV, you put in the acceleration equation that they gave us, which was negative 0.003 v squared. Negative 0.003 v squared dv. Right, so that's you're just dividing by a function. So literally, I just substitute in for that AV what they gave us, and that's negative 0.003 v. And so this v that's right here and this v, they're the same v's. It's kind of weird because one was outside the function and then you substitute in the function, but they're the same v's. And so this could be simplified, right? Just 1 over v basically is what this becomes, right? And then you integrate this. The bounds of this integral are going to be from S1 to SF, right? And this is going to be from V1 to VF. Right? It's going to go from the beginning of the stage to the next stage. And this actually, I called it SF. Let's call this S1 over here. It's not the final. It's the position after that first stage. Right? And then the velocity after that first stage is 400. That was given to us. Okay? So there's all of our things. We have almost everything right now. I guess we could plug some of these in. This S1, that's going to be 1833. SF is what we're after. V1 right here, that V1, that's going to be 400. right? What's the V final going to be? Is that what it says? Down to 100? Yep, 100. So this, yep, good point. I was going to say 0, but I'm glad you're here. You corrected me. It's going to be 100. Right? And what do you do right now? Boop, 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 boop. Right? Put it in your calculator, and it'll solve this for you. Absolutely. You can actually put it in the form, even like you could set in your solver. In your solver, you could say, even if you didn't want to, like if you didn't, I mean, this is just going to be SF minus S1 is what it's going to be. But even if you didn't want to do that, you could still put it in your calculator in that form, and it would tell you that's it. And then in the you have the integral on the left. Inside your solver, get your solver. Inside your solver, you put the integral, and you can set it equal to, and then you put this integral like in that form right there. You don't even have to simplify it. You put it in that form, and you put in those bounds on it, and then you said solve in terms of SF, right? Or whatever you put for that variable in terms of SF, and then it'll just go through and go boop, in about 2 seconds, go boom, SF is this, okay? Okay, play around with that, right? You know, there doesn't sound like I know how to use the TI-89. I could bring in my TI-89 and say, hey, look, everybody, this is how I do a TI-89. But it doesn't sound like many of you have TI-89s. So what you do is YouTube it, right? YouTube, how do you use Solver on my Inspire? How do I use Solver on my TI-89? How do I use a Solver on my, did I say 84 already? Right? It might just laugh at you if you say that. It's like, oh, high school, oh man, right? Upgrade that calculator. I swear to you. I swear to you. Upgrade your calculator. You're going to love it. So if you plug everything in there, what it gives you for the answer here is 22. So SF ends up being equal to 2295.1 meters. Okay. To put that in your, play around with that. Come back to these problems and see if you can get the same answer, plugging stuff into your calculator. Make sure that you can get there, right? And on an exam, something that has solving a quadratic or solving an integral like this, that's going to be fair game. Absolutely fair game, right? And if you want to do it by hand, I mean, like this integral, like 1 over a variable, like what is that? That's like natural log gets involved. Like you don't want to remember how to do that, right? Remember that? Like integral of 1 over x, natural log or something along those lines, right? Like you memorized that back in the day. You don't need to memorize it anymore. Your calculator will do it for you. Okay, with that, and then I'll kind of show you this is another way you could do it. You skip that shortcut of going velocity to position. You actually go through time to do that, but you can get there. And then we'll start talking about curved motion, which is multiple 1D problems. Okay, break. Yeah.
Why you divided S by 2?
Oh, sorry.
Yeah, the spring one.
Oh, okay.
Because you took S and then you divided by 2 because it's like when the spring's out all the way, the velocity is 0.
What did I divide by 2?
Or the 1.228 becomes 0.644.
Oh, that the 0.644 came from. It's different. It's for setting acceleration equal to. So.
Right.
So this one was coming up with the position in which velocity is equal to 0. This is the position where acceleration is equal to 0.
So it's from solving this.
It's from solving this one. Yep, solving this one
Which
gives you
happens
0.6.
to be
Which should be halfway.
Because of that graph.
Yep, that's right. Because it hits it halfway through the cycle. Yep.
So I just wanted to clarify.
Yep. Yeah. So what it does, I mean, really, right, is it goes this way, and about halfway through, it starts decelerating. So it's accelerating, and then here it starts decelerating, and then there it's equal, and then it starts accelerating, and then now the spring's opposite, working the opposite direction, starts decelerating. So it happens at the halfway points is where those max accelerate or max velocities happen. Yep. Yeah.
What's the best place to buy an Inspire?
I don't know. They sell them in the bookstore, and then I try like Amazon and eBay and stuff like that. A lot of people sell like their used ones, right? They're in college and like I don't need this anymore and sell it. So I think like eBay is a good, maybe a good one.
Gotcha.
Yeah, if you trust those guys. Yeah.
Thank you.
Yeah.
I have